Picture yourself throwing a ball straight up into the air. No matter how hard you throw it, eventually it slows, stops, and falls back down. But what if you could throw it hard enough? What if you launched it at such incredible speed that Earth's gravity couldn't pull it back? That critical velocity, the exact speed needed to break free forever, is called escape velocity, and it's one of the most fundamental concepts in physics. Every object in the universe, from pebbles to planets to photons of light, faces this same gravitational challenge. But the journey doesn't end at Earth's edge. Beyond our planet lies a cosmic ladder of escape velocities, each step more extreme than the last, until we reach points so gravitationally intense that nothing, not even light itself, can escape. This is a journey from the familiar pull of Earth to the most remote boundaries physics allows, where the very fabric of space-time bends beyond recognition. The farthest point anything can reach isn't defined by distance alone, but by the fundamental forces that govern motion, energy, and the structure of reality itself. The physics of escape velocity. Escape velocity is the minimum speed an object needs to break free from a celestial body's gravitational pull without any additional propulsion. It's not about going up, it's about going fast enough that gravity's weakening grip can never quite pull you back. The concept emerged from Isaac Newton's law of universal gravitation in the 17th century, though the term itself came later. Newton showed that every object with mass exerts a gravitational force on every other object, and the strength of that force depends on both masses and the distance between them. The farther you travel from a planet or star, the weaker its gravitational pull becomes, but it never quite reaches zero. Escape velocity is the speed at which an object's kinetic energy exactly equals the gravitational potential energy, binding it to the celestial body. The mathematics is surprisingly straightforward. For any spherical object, escape velocity depends only on its mass and radius. The formula derived from energy conservation is the square root of 2 times the gravitational constant times the mass divided by the radius. What this means in practice is that denser, more massive objects have higher escape velocities. A small, dense neutron star has a far higher escape velocity than a giant but diffuse red giant of the same mass. The formula also reveals something counterintuitive. Escape velocity doesn't depend on the mass of the escaping object. A feather and a spacecraft need the same speed to escape Earth, assuming no air resistance. From Earth's surface, that speed is about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. That's more than 30 times the speed of sound. To visualize it, imagine traveling from New York to Los Angeles in less than 4 minutes. No human-made object has ever achieved escape velocity from Earth's surface in a single burst. Instead, rockets accelerate gradually, fighting both gravity and atmospheric drag until they finally break free in the thin upper atmosphere where resistance is minimal. The direction matters less than you might think. Escape velocity is often imagined as launching straight up, but you could theoretically escape by travelling horizontally, or even at an angle downward, as long as you're moving fast enough and don't hit the ground first. In practice, rockets launch vertically to quickly clear the dense lower atmosphere, then gradually tilt toward horizontal to gain the orbital velocity component that helps them escape more efficiently. What happens if you don't quite reach escape velocity? You enter an elliptical orbit, launch at exactly the right speed horizontally from high enough above the atmosphere, and you'll circle the planet forever in a stable orbit. Go a bit faster, and your orbit becomes elongated, stretching farther from the planet at its highest point. Faster still, and that highest point extends beyond the planet's gravitational dominance, you're now on an escape trajectory, even though you started below escape velocity, because you'll be gaining altitude and losing speed until you asymptotically approach zero velocity, infinitely far away. Reach exactly escape velocity, and your orbit becomes a parabola, a path that never quite closes but never quite straightens into a line. Exceed it, and you're on a hyperbolic trajectory, destined to leave the planet's influence with speed to spare. Temperature affects escape velocity in a subtle but crucial way for atmospheres. Gas molecules in a planet's atmosphere move at speeds determined by temperature. The hotter the gas, the faster the molecules. If the temperature is high enough that a significant fraction of molecules reach escape velocity, the atmosphere slowly bleeds away into space. This is why lightweight gases like hydrogen and helium have largely escaped from Earth's atmosphere over billions of years, while heavier molecules like nitrogen and oxygen remain. Mars, with its weaker gravity and thinner atmosphere, lost most of its water vapor and carbon dioxide this way. The Moon, with even lower gravity and no atmosphere to speak of, can't hold on to gases at all. Different celestial bodies present vastly different escape challenges. The Moon's escape velocity is only 2.4 kilometers per second, less than a quarter of Earth's, which is why the Apollo astronauts needed relatively modest rockets to leave the lunar surface. Jupiter, with its enormous mass but also its large radius, has an escape velocity of about 60 kilometers per second. The Sun, despite being 1,000,000 times the volume of Earth, has an escape velocity from its surface of 618 kilometers per second, more than 2 million kilometers per hour. This immense speed reflects both the Sun's huge mass and the fact that its surface, though far from its center, is still within a tremendously strong gravitational field. Escape velocity also explains why we're bound to larger structures. Earth orbits the Sun because it's moving at about 30 kilometers per second fast, but not fast enough to escape the Sun's gravity, which would require 42 kilometers per second at Earth's orbital distance. Similarly, the Sun orbits the center of the Milky Way at roughly 220 kilometers per second, held in place by the combined gravity of hundreds of billions of stars and the vast dark matter halo. To escape the Milky Way from the Sun's position would require speeds exceeding 550 kilometers per second, and the Milky Way itself is bound within the local group of galaxies, which is itself part of larger cosmic structures, each with its own effective escape velocity. The concept extends beyond simple Newtonian gravity. In Einstein's general relativity, gravity isn't a force but a curvature of spacetime. Massive objects bend spacetime around them, and objects moving through that curved space follow paths called geodesics. Escape velocity, in this framework, is the speed needed to follow a geodesic that extends to infinity rather than looping back. Near extremely massive or compact objects, spacetime curves so severely that the escape velocity approaches the speed of light itself, the threshold beyond which we encounter one of the universe's most extreme phenomena. Escaping Earth's gravitational well. Earth's escape velocity of 11.2 kilometers per second represents one of humanity's greatest technological challenges. No object naturally achieves this speed on Earth's surface. The fastest winds barely reach 0.1 kilometers per second. Meteorites entering the atmosphere travel faster, but they're already in space, falling inward rather than escaping outward. To actually leave Earth requires machinery capable of reaching speeds that would vaporize most materials through air friction alone. The challenge begins in the atmosphere itself. Air resistance increases with the square of velocity, meaning that doubling your speed quadruples the drag force. At 11.2 kilometers per second in the lower atmosphere, the compression and friction would generate temperatures exceeding several thousand degrees Celsius, hot enough to melt tungsten. This is why spacecraft and rockets don't attempt to reach escape velocity while still in the thick lower atmosphere. Instead, they accelerate gradually, rising first to where the air is thin before reaching their maximum velocity. Rockets solve the escape velocity problem through staged acceleration. The Saturn V rocket that carried astronauts to the Moon stood 111 meters tall and weighed 2,800 metric tons at launch, but only 45 tons, less than 2% of its initial mass, actually escaped Earth's gravity. The rest was fuel, and empty rocket stages discarded along the way. The first stage burned for just 168 seconds, lifting the rocket to an altitude of 61 kilometers and accelerating it to 2.7 kilometers per second before separating and falling back to Earth. The second stage ignited immediately, burning for another 6 minutes and boosting the speed to 6.8 kilometers per second at an altitude of 185 kilometers. Finally, the third stage fired to achieve orbital velocity, and later to inject the spacecraft onto its path toward the Moon. But orbital velocity isn't the same as escape velocity. To orbit Earth at low altitude requires moving at about 7.8 kilometers per second horizontally, fast enough that as you fall toward Earth, the planet curves away beneath you at the same rate. This is significantly less than the 11.2 kilometers per second needed to escape entirely. Spacecraft headed for the Moon or other planets must perform an additional burn called a translunar injection or transplanetary injection, accelerating from orbital velocity to escape velocity while already high above the atmosphere where air resistance is negligible. The space shuttle, when returning from orbit, re-entered the atmosphere at approximately 8 kilometers per second below escape velocity, but still fast enough to generate surface temperatures of 1,650 degrees Celsius on its heat shield. The shuttle's ceramic tiles absorbed and radiated this heat, protecting the aluminum structure beneath. Objects attempting to leave Earth must be built to withstand similar or greater thermal stresses, plus the mechanical stress of acceleration. Natural objects occasionally escape Earth without rockets. Large asteroid impacts can excavate material and fling it upward at tremendous speeds. Computer simulations show that the impact that created the Chicxulub crater 66 million years ago ejected rocks at velocities exceeding escape velocity. Some of this material would have reached the Moon, Mars, or even escaped the solar system entirely. In fact, meteorites found on Earth that originated from Mars prove that Martian rocks were blasted into space by impacts and eventually fell to our planet. The same process works in reverse. Earth rocks almost certainly rest on the Martian surface. The human body cannot survive the acceleration needed to reach escape velocity quickly. Fighter pilots experience up to 9G during tight maneuvers 9 times Earth's gravitational acceleration, and even with pressure suits, this causes loss of consciousness within seconds. Reaching 11.2 kilometers per second in 1 second would require an acceleration of 11,200 meters per second squared, or about 1,140 G. This would instantly liquefy human tissue. Rockets accelerate much more gently, typically staying below 3 or 4 G, which means they need several minutes of continuous thrust to reach escape velocity. Once free of Earth's gravity well, spacecraft face new challenges. Without continuous propulsion, they follow elliptical orbits around the Sun, shaped by their velocity and position when they escape Earth. The Voyager spacecraft, launched in 1977, achieved solar system escape velocity through a combination of their own rockets and gravitational assists from Jupiter and Saturn. These gravitational slingshots work by having the spacecraft pass close to a massive planet, stealing a tiny fraction of the planet's orbital momentum. For Voyager 1, the Jupiter flyby increased its velocity by about 10 kilometers per second relative to the Sun, enough to eventually escape the solar system entirely. Earth's rotation provides a small but significant assist to launches. The planet's surface at the equator moves eastward at about 0.46 kilometers per second due to rotation. Launching eastward from near the equator means starting with this free velocity, reducing the fuel needed to reach escape velocity by about 4%. This is why launch facilities like those at Kourou in French Guiana, located just 5 degrees north of the equator, are particularly valuable for missions requiring high velocities. Gravity losses also complicate the equation. When a rocket fires its engines while moving upward, some of the thrust goes into fighting gravity rather than increasing velocity. A rocket hovering in place uses maximum thrust but gains no speed. All its energy fights gravity. The longer a rocket takes to reach escape velocity, the more fuel it wastes on gravity losses. This drives rocket design toward powerful, short-duration burns that minimize the time spent fighting gravity. The concept of a space elevator proposes an alternative to rockets, a cable extending from Earth's surface to beyond geostationary orbit, where centrifugal force from Earth's rotation equals gravitational pull. Climbers ascending this cable would gradually gain velocity from Earth's rotation, reaching orbital velocity at geostationary altitude without burning any fuel. Continue beyond, and the climber would be flung outward by centrifugal force, potentially reaching escape velocity with no rocket propulsion at all. Current materials aren't strong enough to build such a structure. Carbon nanotubes show promise but remain far from the required length and consistency. But the physics is sound. Breaking free from the solar system. Escaping Earth's gravity is merely the first step. The Sun's gravitational well is far deeper. At Earth's orbital distance of 150 million kilometers from the Sun, the escape velocity is 42.1 kilometers per second. Since Earth already moves at 30 kilometers per second in its orbit, a spacecraft needs only an additional 12 kilometers per second relative to Earth to escape the solar system. However, this calculation assumes perfect efficiency, launching in exactly the right direction at the right point in Earth's orbit. Real missions require more complex trajectories. The solar system's escape velocity decreases with distance from the Sun, following the same inverse relationship as gravity itself. At Jupiter's orbital distance, solar escape velocity drops to 18.5 kilometers per second. At Neptune's orbit, it's down to 7.7 kilometers per second. This is why missions to the outer solar system often use gravity assists, planetary flybys that steal orbital energy from planets to boost the spacecraft's velocity without burning fuel. The Voyager missions used a rare alignment of the outer planets to perform multiple gravity assists, each one adding velocity and bending their trajectories outward. Only 5 spacecraft have achieved solar system escape velocity: Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. All were launched with tremendous initial velocity and received gravitational assists from the giant planets. Voyager 1, currently the most distant human-made object, is travelling at 17 kilometers per second relative to the Sun and crossed into interstellar space in 2012 when it passed beyond the heliopause, the boundary where the solar wind gives way to the interstellar medium. Despite this, Voyager 1 remains gravitationally bound to the Sun and will continue orbiting for thousands of years, gradually slowing as the Sun's gravity pulls back, though never quite enough to stop it entirely. The New Horizons spacecraft, which flew past Pluto in 2015, was the fastest spacecraft ever launched from Earth, leaving at 16.26 kilometers per second relative to Earth. After its encounter with Pluto, it received a gravitational boost that put it on a trajectory to escape the solar system. It will eventually leave the Sun's gravitational influence entirely, though it will take tens of thousands of years to travel far enough that the Sun's gravity becomes negligible compared to other stars. Natural objects also escape the solar system. Long-period comets arriving from the Oort cloud, a distant shell of icy bodies surrounding the solar system, occasionally pass close enough to Jupiter or another giant planet to receive a gravitational kick that accelerates them beyond solar escape velocity. These comets are flung into interstellar space, never to return. The same process works in reverse. Interstellar objects passing through our solar system can be captured if they lose enough velocity through interactions with planets, though this is exceedingly rare. In 2017, astronomers detected the first confirmed interstellar object passing through the solar system, Oumuamua, a cigar-shaped body moving at 26.3 kilometers per second relative to the Sunday. Its trajectory and speed proved it originated outside our solar system, representing the first direct observation of matter arriving from interstellar space. 2 years later, a second interstellar visitor, the comet Borisov, was detected, confirming that such objects pass through our solar system regularly, though they're difficult to spot because they move so quickly. The Sun itself orbits the center of the Milky Way at approximately 220 kilometers per second, completing one galactic orbit every 230 million years. To escape the Milky Way entirely from the Sun's position would require reaching about 550 kilometers per second, more than twice our current orbital velocity. No spacecraft we've built approaches this speed relative to the galactic center. Even Voyager 1, moving at 17 kilometers per second relative to the Sun, adds only marginally to the Sun's galactic orbital velocity. For practical purposes, all human-made objects remain bound to the Milky Way and will continue orbiting the galactic center for billions of years. Certain stars in the Milky Way move fast enough to escape the galaxy entirely. These hypervelocity stars, traveling at 1,000 kilometers per second or more, were likely accelerated by close encounters with the supermassive black hole at the galactic center or by the explosive destruction of binary star systems. Astronomers have identified several hundred of these stars, all on trajectories that will carry them out of the Milky Way into intergalactic space. Over millions of years, they'll travel farther and farther from the galactic disk, eventually becoming isolated stars drifting through the void between galaxies. The speed of light barrier. As velocities approach the speed of light, 299,792 kilometers per second, in a vacuum, the physics of escape velocity transforms fundamentally. In Newtonian mechanics, there's no theoretical upper limit to velocity. Add enough energy, and an object moves arbitrarily fast. But Einstein's special relativity, published in 1905, revealed that the speed of light is an absolute cosmic speed limit, the same in all reference frames, and that approaching it requires exponentially increasing amounts of energy. The reason lies in the relationship between energy, mass, and velocity. As an object accelerates, its relativistic mass increases not because it's gaining matter, but because energy and mass are equivalent through Einstein's famous equation. The faster something moves, the more energy is locked into its motion, effectively increasing its inertia. At 90% of light speed, an object's relativistic mass is 2.29 times its rest mass. At 99%, it's 7.09 times. At 99.9%, 22.4 times. The progression becomes steeper with each increase, and reaching exactly the speed of light would require infinite energy. Only massless particles like photons travel at light speed. They have no rest mass and always move at exactly 299,792 kilometers per second in a vacuum, regardless of the observer's motion. Photons can never be at rest. The concept is meaningless for them, and they experience no passage of time from their own perspective. From a photon's point of view, if such a thing could be said to exist, emission and absorption happen instantaneously, even if billions of years pass in our reference frame. For massive objects, accelerating to near light speeds requires particle accelerators. The Large Hadron Collider accelerates protons to 99.9999991% of light speed, giving them energies of 6.5 trillion electron volts. At this velocity, each proton's relativistic mass increases by a factor of 7,460. The protons circle the 7-kilometer ring about 11,000 times per second, held in their circular path by superconducting magnets. Despite their incredible speed, they can never quite reach light speed. Additional energy produces diminishing returns in velocity, instead piling into the increasing relativistic mass. In the context of escape velocity, relativity adds complications. Near a massive object like a neutron star or black hole, spacetime itself is curved. Light travelling outward from such an object is redshifted, stretched to longer wavelengths because it's climbing out of a gravitational well, losing energy in the process. The more massive and compact the object, the greater this gravitational redshift. For photons escaping from just above a black hole's event horizon, the redshift becomes infinite. They lose all their energy and can never escape, even though they're travelling at light speed. This leads to one of the universe's most extreme conditions, a region where escape velocity equals or exceeds the speed of light. Since nothing can move faster than light, nothing, not matter, not energy, not information, can escape from such a region. This is the defining characteristic of a black hole. The boundary where escape velocity reaches exactly the speed of light is the event horizon, a one-way membrane in spacetime. Cross it moving inward, and no force in the universe can bring you back out. The Schwarzschild radius defines the size of this event horizon for a non-rotating black hole. It depends only on mass. Every solar mass adds about 3 kilometers to the radius. A black hole with the mass of our Sun would have an event horizon roughly 6 kilometers in diameter, incredibly small for such an enormous mass. The supermassive black hole at the center of the Milky Way, with about 4 million solar masses, has an event horizon approximately 24 million kilometers across, smaller than the orbit of Mercury but containing the mass of millions of stars. Outside the event horizon, photons can still escape, though they lose energy climbing out of the gravitational well. An observer far from a black hole watching a light source fall inward would see the light becoming redder and dimmer as the source approaches the event horizon. Time dilation also stretches the light wave's clocks near the event horizon, run slower from the perspective of distant observers. At the horizon itself, time appears to stop entirely. The infalling object seems frozen in place, its light stretched to infinite wavelengths, effectively disappearing from view. From the object's own perspective, however, nothing special happens at the event horizon it falls through in finite time. Unaware that it's crossed the point of no return until the tidal forces near the singularity rip it apart. Neutron stars and extreme gravity. Before reaching black holes, we encounter neutron stars objects so dense that their escape velocities approach but don't quite reach the speed of light. A neutron star is the collapsed core of a massive star that exploded as a supernova. During the collapse, protons and electrons are crushed together to form neutrons, and the entire star's core, containing 1.4 to 2 times the mass of the Sun, compresses into a sphere only 20 to 25 kilometers across. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. the escape velocity from a neutron star's surface reaches approximately 100,000 to 150,000 kilometers per second, 1/3 to 1/2 the speed of light. This is high enough that relativistic effects become significant. Light escaping from the surface loses substantial energy to gravitational redshift, emerging with longer wavelengths than when it was emitted. Time passes measurably slower on the surface of a neutron star, compared to far from it. A clock there would tick at roughly 70 to 80%, the rate of a clock in deep space. These extreme conditions create observable effects. Neutron stars that rotate rapidly and emit beams of radiation are called pulsars. As the star spins, these beams sweep across space like lighthouse beacons. Astronomers detect pulsars as precisely timed radio pulses, some repeating hundreds of times per second. The fastest known pulsar, PSR J17482446 AD, rotates 716 times per second, meaning its equator moves at roughly 24% of light speed. At such velocities, matter at the surface experiences tremendous centrifugal force, yet the neutron star's gravity holds it in place, a testament to the extraordinary binding energy. Matter accreting onto a neutron star releases enormous energy. Gas falling from a companion star spirals inward, forming an accretion disk that heats to millions of degrees, emitting X-rays detectable across the galaxy. As this material crashes into the neutron star's surface at substantial fractions of light speed, it releases gravitational potential energy with terrifying efficiency. The energy yield per kilogram of infalling matter approaches 10% of its mass energy, far exceeding the 0.7% efficiency of hydrogen fusion in the Sun's core. The surface of a neutron star is anything but smooth. The intense magnetic fields trillions of times stronger than Earth's channel material into hot spots at the magnetic poles. The crust, composed of atomic nuclei and electrons packed into a crystalline lattice, is the hardest material in the universe, billions of times stronger than steel. Below the crust lies a superfluid of neutrons, a quantum state where viscosity vanishes and the liquid flows without resistance. Deeper still, conditions become so extreme that the physics remains uncertain. Hypothesized forms of matter include quark-gluon plasmas, or even exotic states where quarks break free from neutrons entirely. Gravitational waves provide a new window into neutron star physics. In 2017, the LIGO and Virgo detectors observed gravitational waves from two neutron stars spiraling together and merging. The event, located 130 million light-years away, released more energy in gravitational waves in its final seconds than all the stars in the observable universe combined emitted as light. The merger created a kilonova, an explosion powered by the radioactive decay of heavy elements synthesized in the collision. Spectroscopic analysis of the kilonova's light confirmed the production of gold, platinum, and other heavy elements, revealing that neutron star mergers are the primary source of these materials in the universe. Some neutron stars may possess escape velocities even higher than typical values. Theoretical models suggest that the most massive neutron stars, approaching the upper mass limit around 2.2 solar masses, could have surface escape velocities reaching 200,000 kilometers per second, 2/3 the speed of light. Beyond this mass limit, no known force can prevent further collapse. The star implodes catastrophically, its escape velocity exceeding the speed of light, and a black hole forms. The event horizon. The event horizon is not a physical surface, but a mathematical boundary in spacetime, the point of no return surrounding a black hole. It's the sphere where escape velocity exactly equals the speed of light. Inside this boundary, all paths through spacetime lead inward toward the singularity. Outside, escape is possible. At the horizon itself, even light travelling directly outward makes no progress. It remains frozen at the boundary, unable to climb out of the gravitational well. For a non-rotating black hole, the event horizon is a perfect sphere with radius determined by the Schwarzschild solution to Einstein's field equations. This radius depends only on mass. Larger black holes have proportionally larger horizons. A stellar mass black hole of 10 solar masses has an event horizon about 30 kilometers in radius. The supermassive black hole in the galaxy M87, imaged by the Event Horizon Telescope in 2019, has a mass of 6.5 billion solar masses and an event horizon roughly 20 billion kilometers across, larger than the orbits of Neptune. Crossing the event horizon is a one-way trip, but nothing locally dramatic happens there. An astronaut falling into a supermassive black hole would pass through the event horizon without feeling anything unusual at that moment. There's no wall, no barrier, no surface to strike. The horizon is simply the last place from which light can escape to the outside universe. Once across, the astronaut could still see outward light from the external universe. They can cross the horizon inward, but any signal the astronaut sends outward is pulled back toward the singularity. From outside, however, the crossing looks very different. An observer watching someone fall into a black hole sees them slow down as they approach the event horizon. Time dilation becomes increasingly severe. The falling person's clock appears to tick slower and slower. Their image becomes redder as light loses energy climbing out of the deepening gravitational well. They dim and fade, asymptotically approaching the horizon but never quite crossing it from the external observer's perspective. In principle, their image would remain frozen at the event horizon forever, though in practice it becomes too faint to detect within seconds. This creates an apparent paradox. The infalling observer crosses the horizon in finite proper time, but an external observer never sees the crossing happen. Both perspectives are correct within their own reference frames. The resolution lies in the relativity of simultaneity events that are simultaneous in one reference frame are not simultaneous in another, especially in strong gravitational fields. Real black holes rotate, and rotating black holes are more complex. The Kerr solution describes a rotating black hole with two event horizons, an outer and an inner, and an additional boundary called the ergosphere. In the ergosphere, space-time itself is dragged around the black hole so forcefully that remaining stationary is impossible. Everything must rotate with the black hole, though escape is still possible from this region. The event horizon of a rotating black hole is oblate rather than spherical, flattened at the poles and bulging at the equator due to centrifugal effects. The maximum rotation rate for a black hole is determined by the requirement that the event horizon exists. Beyond this limit, the singularity would be naked exposed to the outside universe, violating the cosmic censorship hypothesis, which states that singularities must always be hidden behind event horizons. Observations suggest that real black holes can rotate very rapidly, with some spinning at more than 90% of the theoretical maximum. The black hole in M87 rotates once every few days, despite its enormous size, carrying the surrounding spacetime with it in a phenomenon called frame dragging. The event horizon also marks the boundary of where information can return from. According to classical general relativity, anything crossing the horizon is lost forever. Its information cannot escape. This created the black hole information paradox when combined with quantum mechanics, which insists that information cannot be destroyed. Stephen Hawking's discovery of Hawking radiation partially resolved this. Black holes emit thermal radiation due to quantum effects near the event horizon, slowly evaporating over time. The radiation carries energy away, causing the black hole to lose mass. Over immense timescales, even supermassive black holes will evaporate completely, though the process takes far longer than the current age of the universe for black holes of stellar mass or greater. Inside the event horizon, beyond the event horizon lies a region inaccessible to observation, knowable only through theoretical physics. Inside, space and time exchange roles in a certain mathematical sense. The radial direction toward the singularity becomes time-like. Moving toward the center is as inevitable as moving forward in time outside the horizon. The temporal direction becomes space-like. An observer inside can no more avoid reaching the singularity than someone outside can avoid moving into the future. The proper time from crossing the horizon to reaching the singularity depends on the black hole's mass. For a stellar mass black hole, the journey takes microseconds. For a supermassive black hole, an infalling observer might have hours. The singularity itself is not a point in space but a moment in time, an inevitable future for everything inside the horizon. General relativity predicts that all infalling matter and energy are crushed to infinite density at the singularity, where space-time curvature becomes infinite and the known laws of physics break down. Tidal forces intensify dramatically as an object approaches the singularity. The gravitational pull on the nearer part of an object exceeds the pull on the farther part by an ever-increasing amount. For a stellar mass black hole, these tidal forces become lethal well before crossing the event horizon. A human falling feet first would be stretched vertically, and compressed horizontally, spaghettified by tidal stresses millions of times stronger than any material can withstand. For supermassive black holes, the tidal forces at the event horizon are much weaker due to the larger radius, allowing an astronaut to cross intact, though they would still be destroyed closer to the singularity. Inside a rotating black hole, the structure becomes more exotic. The Kerr solution predicts an inner horizon surrounding a ring-shaped singularity. The region between the inner and outer horizons is unstable. Small perturbations grow catastrophically. Beyond the inner horizon lies the ring singularity, a circle of infinite density rotating at the black hole's equator. Unlike the point singularity of a non-rotating black hole, the ring singularity might permit passages through its center, leading to speculative possibilities like connections to other regions of spacetime or even other universes. These inner structures are probably unrealistic. Quantum effects, which general relativity doesn't account for, likely dominate at such extreme scales. The singularity represents the breakdown of classical physics, not a real physical object. Physicists expect that a complete theory of quantum gravity, perhaps string theory, loop quantum gravity, or another framework, would replace the singularity with some form of quantum spacetime structure. The Planck scale, at 10 to the power of minus 35 meters and 10 to the power of minus 43 seconds, is thought to be the smallest meaningful length and time in physics. At these scales, spacetime may be granular or possess a foamy structure, preventing the formation of true singularities. Observations from outside provide indirect evidence about black hole interiors. The masses and spins of black holes measured through their gravitational effects on nearby matter are consistent with general relativity's predictions. Gravitational wave signals from merging black holes match the theoretical waveforms calculated from the Kerr metric. The shadows cast by black holes, as imaged by the Event Horizon Telescope, show the expected size and shape. All evidence supports the idea that event horizons exist and behave as relativity predicts, though direct confirmation of the interior structure remains impossible. Hawking radiation and black hole evaporation. In 1974, Stephen Hawking made a startling discovery. Black holes are not entirely black. Quantum mechanical effects near the event horizon cause black holes to emit thermal radiation, now known as Hawking radiation. This phenomenon arises from the uncertainty principle, which permits temporary violations of energy conservation particle-antiparticle pairs can spontaneously appear in a vacuum, borrowing energy from the quantum field as long as they annihilate quickly enough. Near a black hole's event horizon, one member of such a pair can fall into the black hole while the other escapes. To an outside observer, the black hole appears to emit radiation. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass black holes have temperatures of mere billionths of a Kelvin, far colder than the cosmic microwave background. They absorb far more energy from the universe than they emit, so they grow rather than shrink. But smaller black holes are hotter. A black hole with the mass of the Moon would have a temperature of about 3 Kelvin. One with the mass of a large asteroid would glow in the infrared. A black hole with the mass of a mountain would radiate invisible light and would be as hot as the sun's surface. As a black hole emits Hawking radiation, it loses mass and its temperature increases. This creates a runaway process. The hotter it gets, the more it radiates, losing mass faster and getting hotter still. Eventually, the black hole evaporates completely in a final burst of radiation. The timescale for evaporation is proportional to the cube of the mass. A solar mass black hole would take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. A supermassive black hole would take even longer. But a primordial black hole with a mass of 100 million tons, formed in the early universe, would be evaporating right now, its lifetime matching the current age of the cosmos. No primordial black holes of this mass have been detected, suggesting they're either very rare or don't exist. Larger primordial black holes may constitute part or all of the universe's dark matter, though current constraints from various observations make this unlikely. The smallest primordial black holes would have evaporated long ago, perhaps contributing to the diffuse background radiation permeating the universe. Hawking radiation carries profound implications for black hole thermodynamics. A black hole has entropy proportional to the area of its event horizon, measured in Planck units. This entropy is enormous. A solar mass black hole has entropy exceeding 10 to the power of 54, vastly greater than the entropy of the star it formed from. When a black hole evaporates, its entropy is transferred to the outgoing radiation. The total entropy of the universe increases, in accordance with the second law of thermodynamics. The information paradox arises from the thermal nature of Hawking radiation. Thermal radiation appears to carry no information about what fell into the black hole. It's characterized only by temperature, which depends solely on the black hole's mass. If a black hole forms from matter and then evaporates into featureless thermal radiation, information about the original matter seems to be destroyed, violating quantum mechanics' fundamental principle that information is conserved in physical processes. Proposed resolutions include the possibility that information is encoded in subtle correlations in the Hawking radiation, imperceptible in practice but present in principle. Another proposal suggests that information is preserved in the black hole's internal structure and released in the final stages of evaporation. The holographic principle posits that all information about the interior is encoded on the event horizon itself, like a hologram, and is gradually transferred to the radiation. String theory suggests that black holes are ultimately composed of fundamental strings, and information is preserved in the strings' quantum states. None of these proposals is fully verified, and the information paradox remains an active area of research at the intersection of quantum mechanics and gravity. The photon sphere. Just outside the event horizon of a black hole lies another critical boundary, the photon sphere. This is the orbital radius where gravity is so strong that light can orbit the black hole in circular paths. For a non-rotating black hole, the photon sphere is located at 1.5 times the Schwarzschild radius. At this distance, photons travelling tangentially to the surface can circle the black hole indefinitely, though the orbit is unstable. A slight inward deviation causes the photon to spiral into the black hole, while a slight outward deviation allows it to escape to infinity. The photon sphere is not a physical surface but a mathematical shell where the curvature of spacetime bends light into closed loops. An observer hovering at the photon sphere could theoretically see the back of their own head. Light from the back of their head would circle the black hole and return to their eyes. In practice, turbulence and the instability of photon orbits would make this impossible. The photon sphere is crucial for understanding black hole shadows. When the Event Horizon Telescope imaged the black hole in M87, what appeared as the dark central region was not the event horizon itself but the photon sphere. Light from the accretion disk swirling around the black hole bent around the photon sphere, creating a bright ring of emission. The shadow, the dark zone in the center, corresponds to photons that cross the photon sphere on inward trajectories, captured by the black hole's gravity. The shadow's size is approximately 2.6 times the Schwarzschild radius, determined by the paths of light rays that barely miss capture. Inside the photon sphere, but outside the event horizon, lies a region where light can escape, but only if aimed outward precisely enough. Photons emitted horizontally or inward will curve back and fall into the black hole. The closer to the event horizon, the narrower the cone of escape trajectories becomes. Exactly at the horizon, the escape cone collapses to zero, no outward direction permits escape. For rotating black holes, the photon sphere is replaced by a more complex structure. Frame dragging causes the paths of photons moving with the black hole's rotation to differ from those moving against it. Prograde photons, those orbiting in the same direction as the black hole's spin, can orbit closer to the event horizon than retrograde photons. This creates an asymmetry in the black hole's shadow, observable in high-resolution images. The Event Horizon Telescope's image of M87 showed subtle asymmetries consistent with a rotating black hole, though the rotation rate could not be precisely determined from that image alone. The photon sphere also affects the appearance of objects near the black hole. An accretion disk viewed from above appears distorted. The portion of the disk on the far side is bent upward by gravitational lensing, becoming visible to an observer above the disk. The disk appears to wrap up and over the black hole, creating multiple images of the same material at different angles. The Doppler effect from the disk's orbital motion also creates asymmetries. Material moving toward the observer appears brighter and blue-shifted, while material moving away is dimmer and red-shifted, producing a characteristic appearance of a bright crescent on one side. Gravitational lensing and spacetime curvature. Massive objects bend the fabric of spacetime, curving the paths of light passing nearby. This phenomenon, called gravitational lensing, was predicted by Einstein's general relativity and first observed during a solar eclipse in 1919, when stars appeared to shift position due to the sun's gravity bending their light. The effect becomes far more dramatic near black holes and neutron stars, where space-time curvature is extreme. Light from a distant star passing close to a massive object is deflected, bending around the object in a curved arc. If the alignment is perfect, the observer, the massive object, and the distant star are perfectly collinear. The star's light is bent into a complete circle around the lens, forming an Einstein ring. More commonly, the alignment is imperfect, producing multiple distorted images of the background object or stretching its image into arcs. Gravitational lensing by galaxy clusters magnifies and distorts the images of more distant galaxies located behind them. The Hubble Space Telescope has captured spectacular images of galaxy clusters acting as cosmic magnifying glasses, revealing faint, distant galaxies that would otherwise be undetectable. This effect has enabled the observation of some of the earliest galaxies in the universe, formed less than 1 billion years after the Big Bang. Near black holes, lensing becomes so strong that multiple images of the same object appear at different locations around the black hole. An accretion disk, for example, produces a direct image visible to an observer, plus additional images of the far side of the disk bent around the black hole's gravity. These secondary images are fainter and more distorted than the primary image, stacked at progressively higher angles above the black hole. In principle, infinite images exist, each corresponding to light that has circled the black hole an additional number of times before reaching the observer, though each successive image is exponentially dimmer. The bending of light near massive objects allows measurement of their masses. By observing how much a cluster of galaxies distorts the images of background galaxies, astronomers can map the cluster's total mass distribution, including dark matter. These lensing maps reveal that dark matter outweighs visible matter by roughly 5-1, and that it forms extended halos around galaxies and clusters, precisely as predicted by cosmological models. Microlensing events occur when a foreground star or planet passes almost directly in front of a background star. The gravitational field of the foreground object focuses the light from the background star, causing a temporary brightening. These events have been used to detect exoplanets orbiting distant stars. The planet's gravity adds a brief additional brightening on top of the star's lensing signal. Thousands of microlensing events have been observed, revealing planets, brown dwarfs, and even isolated black holes drifting through the galaxy. Time delays from gravitational lensing provide another measurable effect. Light taking different paths around a massive lens travels different distances and through regions of different gravitational potential. This causes the paths to have different travel times. For quasars lensed by galaxies, multiple images of the same quasar can vary in brightness at different times, offset by days to months, corresponding to the time delay between the different light paths. These delays allow astronomers to measure the expansion rate of the universe through a method independent of standard candles or cosmic distance ladders. Gravitational lensing reaches its extreme form near black holes. Light grazing the photon sphere is bent by almost 180 degrees, allowing an observer to see around the black hole. Light passing slightly farther out is bent less severely, but still enough to create multiple windings around the black hole before escaping. This effect contributes to the bright ring seen in black hole images, photons, from the accretion disk spiral around the black hole multiple times, creating nested layers of emission. Wormholes and exotic spacetime. General relativity permits solutions that include wormholes, hypothetical tunnels connecting distant regions of spacetime. The simplest wormhole, called an Einstein-Rosen bridge, arises from the Schwarzschild solution extended to its fullest mathematical form. This extension reveals that the spacetime of a non-rotating black hole connects to a white hole, a region from which nothing can enter but everything must exit, the time-reversed counterpart of a black hole. The bridge connecting them is a wormhole. However, this wormhole is not traversable. It forms and collapses so quickly that not even light can cross from one side to the other. Any attempt to enter from one end causes the wormhole to pinch off before the traveller reaches the other end, trapping them inside a black hole instead. For a wormhole to be traversable, it must be held open by exotic matter with negative energy density matter that violates the usual energy conditions of general relativity. Negative energy sounds impossible, but quantum field theory permits it under special circumstances. The Casimir effect, for example, involves two parallel conducting plates in a vacuum. Quantum fluctuations outside the plates contribute more pressure than fluctuations between the plates, creating a net attractive force equivalent to negative energy density between the plates. Unfortunately, the amount of negative energy produced this way is minuscule, far too small to hold open a macroscopic wormhole. Even if exotic matter could stabilize a wormhole, other problems arise. Traversable wormholes can, in principle, be used to construct closed time-like curves paths through spacetime that loop back to their own past, permitting time travel. This creates potential paradoxes, such as the grandfather paradox. Attempts to resolve these paradoxes often invoke the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics prevent the formation of closed time-like curves, possibly through quantum effects that destroy any wormhole on the verge of becoming a time machine. No observational evidence supports the existence of wormholes. If they existed, they would produce distinctive gravitational lensing patterns different from those of black holes or ordinary matter concentrations. Searches for such signatures have found nothing. Wormholes remain purely speculative, mathematical curiosities allowed by general relativity, but perhaps forbidden by a more complete theory. Incorporating quantum effects, other exotic spacetime structures include cosmic strings, hypothetical one-dimensional defects in spacetime formed during phase transitions in the early universe. A cosmic string's gravitational field creates a conical deficit in spacetime. Two objects on opposite sides of a cosmic string can reach each other along paths shorter than the Euclidean distance, effectively allowing faster-than-light travel in a certain sense, though not violating relativity because spacetime itself is shaped unusually. Cosmic strings could also create double images of distant objects due to lensing, though no confirmed observations exist. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a hypothetical faster-than-light propulsion system, consistent with general relativity. The idea involves contracting spacetime in front of a spacecraft and expanding it behind, creating a warp bubble that carries the ship forward faster than light relative to external space, without the ship itself moving faster than light through its local spacetime. The ship surfs on a wave of spacetime. However, creating such a warp bubble requires exotic matter with negative energy density, and the energy requirements are astronomical. Estimates range from the mass energy of the observable universe to merely the mass of Jupiter, depending on proposed refinements. Even if possible, causality violations might arise, and quantum effects might destabilize the warp bubble. The Schwarzschild radius. The Schwarzschild radius defines the boundary of a non-rotating black hole's event horizon. It's the radial coordinate, where the escape velocity equals the speed of light, calculated from the Schwarzschild metric solution to Einstein's field equations. For a spherically symmetric, non-rotating mass, the Schwarzschild radius is proportional to the mass, specifically about 3 kilometers per solar mass. A 1 solar mass black hole has a Schwarzschild radius of approximately 3 kilometers. Earth, if compressed to a black hole, would have a Schwarzschild radius of about 9 millimeters smaller than a marble. The Moon's would be about 0.1 millimeters. Jupiter's would be roughly 2.8 meters. The Sun's is about 3 kilometers, as noted. These calculations reveal the extraordinary densities required to form black holes from ordinary astronomical objects. Earth's average density is 5.5 grams per cubic centimeter. But to become a black hole, its entire mass would need to fit within a sphere 9 millimeters in radius, implying a density exceeding 2 trillion grams per cubic centimeter. Stellar mass black holes form from the collapse of massive stars. When a star with more than 25 solar masses exhausts its nuclear fuel, its core collapses catastrophically. If the core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, beyond which even neutron degeneracy pressure cannot resist gravity, nothing can halt the collapse. The core compresses past the neutron star stage, past the point where escape velocity reaches light speed and forms a black hole. The outer layers of the star may be ejected in a supernova or may fall into the black hole depending on the collapse dynamics. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, are hypothesized to exist in dense star clusters, or as the seeds of supermassive black holes, though direct evidence is limited. Their Schwarzschild radii range from hundreds to hundreds of thousands of kilometers. Detecting them is challenging because they're less common than stellar mass black holes and less luminous than actively feeding supermassive black holes. Supermassive black holes occupy the centers of most galaxies. These giants contain millions to billions of solar masses, with Schwarzschild radii measured in millions to billions of kilometers comparable to planetary orbits. The supermassive black hole in the Milky Way, Sagittarius A star, has about 4 million solar masses and a Schwarzschild radius of roughly 12 million kilometers, about 17 times the Sun's physical radius. The black hole in M87, imaged by the Event Horizon Telescope, has 6.5 billion solar masses and a Schwarzschild radius around 20 billion kilometers, more than 4 times Neptune's orbital radius. How supermassive black holes form remains an open question. They cannot form directly from stellar collapse. No single star is massive enough. Proposed formation mechanisms include the merger of many stellar mass black holes over billions of years, direct collapse of massive gas clouds in the early universe, or runaway stellar collisions in dense star clusters. Observations of quasars powered by supermassive black holes existing less than 1 billion years after the Big Bang suggest that rapid growth mechanisms must operate, possibly involving sustained super-Eddington accretion, where matter falls in faster than radiation pressure can expel it. The Schwarzschild radius also defines gravitational time dilation. A clock at the Schwarzschild radius, if somehow held stationary there, would appear from far away to stop entirely its ticks infinitely redshifted. This infinite time dilation reflects the fact that the Schwarzschild radius is the event horizon, where the coordinate time required for an event becomes infinite from the perspective of a distant observer. For an observer at a finite distance above the Schwarzschild radius, time dilation is finite but severe. At twice the Schwarzschild radius, a clock ticks at about 71% the rate of a distant clock. At 10 times the Schwarzschild radius, the rate is about 95%. Tidal forces at the Schwarzschild radius depend on the black hole's mass. For a solar mass black hole, tidal forces at the event horizon are catastrophically strong, about 10 to the power of 14 meters per second squared per meter of separation, enough to tear apart atomic nuclei. For a supermassive black hole, tidal forces at the event horizon are much weaker, inversely proportional to the square of the mass. An astronaut could cross the event horizon of a billion solar mass black hole without experiencing lethal tidal forces, though they would be doomed once inside, eventually succumbing to tidal forces closer to the singularity. Cosmic censorship and naked singularities. The cosmic censorship hypothesis, proposed by Roger Penrose in 1969, states that singularities, regions of infinite density where general relativity breaks down, must always be hidden behind event horizons. In other words, nature forbids naked singularities visible to external observers. This hypothesis is not proven, but is widely believed because its violation would create severe problems for predictability in physics. If singularities could be observed, arbitrary information could emerge from them, making the universe fundamentally unpredictable. The weak cosmic censorship hypothesis states that singularities cannot be visible from far away, they must be hidden inside event horizons. The strong cosmic censorship hypothesis makes a bolder claim. Spacetime cannot be extended beyond the singularity in any physically reasonable way, preventing any observer, even one falling into a black hole, from extracting information from the singularity to influence the external universe. Certain solutions to Einstein's equations seem to permit naked singularities. A rotating black hole spinning faster than the maximum allowed rate, or a charged black hole with charge exceeding its mass in appropriate units, would have no event horizon, exposing its singularity. However, physical processes appear to prevent such extremes. Adding charge to a black hole increases repulsion, making further charge addition difficult. Spinning a black hole up by adding angular momentum eventually causes it to shed angular momentum through gravitational wave emission or by ejecting matter. Natural processes seem to keep black holes within limits that preserve cosmic censorship. Attempts to create naked singularities in computer simulations generally fail. When matter is arranged to collapse in ways that might form a naked singularity, the simulations show that event horizons form just in time to hide the singularity, or the collapse halts before reaching infinite density. These results support cosmic censorship but do not prove it universally. Quantum effects might also enforce cosmic censorship. As matter collapses toward infinite density, quantum mechanics should become important at the Planck scale. A full theory of quantum gravity might replace the classical singularity with a quantum structure that doesn't involve infinite density, eliminating the issue. Alternatively, quantum fluctuations near a would-be naked singularity might generate an event horizon through back reaction effects on spacetime geometry. If naked singularities existed, they would produce observable signatures. Gravitational lensing near a naked singularity would differ from that around a black hole. Accretion of matter onto a naked singularity might produce distinctive radiation patterns. Searches for such phenomena have found no convincing candidates. All compact objects massive enough to be black holes appear to possess event horizons, consistent with cosmic censorship. The debate extends to the interior of rotating black holes. The Kerr solution contains a ring singularity surrounded by an inner horizon. Some physicists argue that the inner horizon is unstable and would collapse or be destroyed by quantum effects, preventing any observer from reaching the ring singularity. Others suggest that the inner horizon and ring singularity are artifacts of idealizing the black hole as perfectly isolated, and that realistic black holes within falling matter and radiation would have different interior structures. The innermost stable circular orbit. Around any massive object, there exists an innermost stable circular orbit, the smallest radius at which an object can orbit without spiraling inward. For planets orbiting the Sun or satellites orbiting Earth, this limit is essentially at the object's surface, irrelevant for practical purposes. Near black holes and neutron stars, however, the ISCO is located well above the surface or event horizon, playing a critical role in accretion dynamics. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius, about 9 kilometers per solar mass. Anything orbiting closer is unstable. Any small perturbation causes the orbit to decay rapidly, with the object spiraling into the black hole within a few orbits. At the ISCO, an orbiting object moves at about half the speed of light. Inside the ISCO, even light cannot orbit stably. Only the photon sphere at 1.5 Schwarzschild radii permits brief circular photon paths, and those are unstable. For rotating black holes, the ISCO's location depends on whether the orbit is prograde or retrograde. Prograde orbits, moving with the black hole's spin, can be stable closer to the event horizon, approaching the horizon itself for maximally spinning black holes. Retrograde orbits are stable, only farther out. This asymmetry results from frame dragging. The black hole's rotation drags spacetime around with it, assisting prograde orbits and resisting retrograde ones. Accretion disks around black holes extend inward to the ISCO. Gas spirals inward through the disk, gradually losing angular momentum and energy through viscous friction, heating as it goes. Near the ISCO, the disk reaches its maximum temperature, emitting X-rays and extreme ultraviolet light. At the ISCO, gas suddenly loses stability and plunges into the black hole, releasing any remaining energy in a final burst of radiation. The difference in ISCO location between rotating and non-rotating black holes affects the disk's emission spectrum, allowing astronomers to measure black hole spins. The spin of the black hole in Mir 87 has been estimated from the structure of its X-ray emission. Observations suggest it rotates at a significant fraction of the maximum rate, with the ISCO located close to the event horizon. This rapid rotation may be sustained by sustained accretion of matter with angular momentum aligned with the black hole's spin. Neutron stars also have ISCOs, determined by their mass and radius. For a typical one, 4. Solar, mass neutron star with a radius of about 12 kilometers, the ISCO is located around 18 kilometers from the center, just above the star's surface. Matter in an accretion disk around a neutron star spirals inward to the ISCO, then crashes onto the solid surface, releasing energy in a different manner than accretion onto a black hole. The impact heats the surface to millions of degrees, producing X-ray emission and sometimes thermonuclear explosions called X-ray bursts. The ISCO's location also determines the efficiency of accretion as a power source. For a non-rotating black hole, matter falling from the ISCO to the event horizon releases about 6% of its rest mass as energy. For a maximally rotating black hole, where the ISCO is much closer to the horizon, the efficiency reaches about 42%. This makes black hole accretion one of the most efficient energy generation processes in the universe, far exceeding nuclear fusion. Extreme mass ratio in spiral systems where a stellar mass object orbits a supermassive black hole provide tests of general relativity. As the small object spirals inward, it emits gravitational waves that encode information about the spacetime geometry. Future space-based gravitational wave detectors like LISA will observe these systems, mapping the spacetime around supermassive black holes with exquisite precision and testing whether general relativity holds in the strong field regime near the ISCO. Gravitational waves and merging black holes. Gravitational waves are ripples in spacetime caused by accelerating masses. Predicted by Einstein in 1916, they remained undetected for a century. The first direct detection came on the 14th of September 2015, when the LIGO observatories recorded gravitational waves from two merging black holes located 1.3 billion light-years away. This observation opened a new window into the universe, revealing events invisible to electromagnetic telescopes. Gravitational waves propagate at the speed of light, carrying energy away from their source. They stretch and compress spacetime transversely to their direction of travel, briefly changing distances between objects. The effect is extraordinarily weak. The black hole merger detected by LIGO produced gravitational waves that changed distances on Earth by less than 1/10,000th the diameter of a proton. Detecting such minute distortions required laser interferometers with arm lengths of 4 kilometers and sensitivity capable of measuring displacements far smaller than an atomic nucleus. The signal from merging black holes has a characteristic pattern called a chirp. As the black holes spiral together, they orbit faster and faster, emitting gravitational waves at increasing frequency. The waveform encodes the masses and spins of the black holes. Shortly before merger, the frequency rises into the range detectable by LIGO, tens of hertz climbing rapidly to hundreds of hertz at the moment of merger. The amplitude peaks as the black holes coalesce, then damps away as the merged black hole's event horizon settles into a stable configuration, a process called ring-down. The entire detected signal lasts only a fraction of a second, but it encodes detailed information about the system. The first detected merger involved black holes of 36 and 29 solar masses, producing a final black hole of 62 solar masses. The missing 3 solar masses, equivalent to the mass energy of 3 suns, was radiated as gravitational waves during the final fraction of a second. This energy release exceeded the combined light output of all the stars in the observable universe during the merger, though it was emitted in gravitational waves rather than light, making it invisible to conventional telescopes. Subsequent detections have revealed a population of merging black holes with diverse masses and spins. Some mergers involve black holes in the gap between stellar mass and supermassive black holes, suggesting intermediate mass black holes exist. Mergers of black holes with very different masses produce asymmetric signals. Spins misaligned with the orbital plane create more complex waveforms. Each detection refines our understanding of black hole populations and formation mechanisms. Neutron star mergers also emit gravitational waves. In 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars merging 130 million light-years away. Unlike black hole mergers, this event produced electromagnetic radiation, gamma rays, X-rays, optical light, infrared, and radio waves detected by telescopes worldwide. The combined observations confirmed that neutron star mergers synthesize heavy elements like gold and platinum, resolving a long-standing question about the origin of these elements. The in-spiral phase of a merger is governed by the loss of orbital energy to gravitational wave emission. As the objects lose energy, they move closer together and orbit faster, emitting stronger gravitational waves which causes them to still lose energy faster. The process accelerates exponentially. For 2 solar mass black holes starting in a wide orbit, the in-spiral might take millions of years. Once they reach close proximity, the final merger happens in milliseconds. At the moment of merger, space-time near the black holes is dynamically curved. Neither black hole has a well-defined event horizon in the traditional sense. General relativity permits the calculation of the merger's dynamics through numerical simulations, solving Einstein's equations on supercomputers. These simulations show that the event horizons merge, forming a single, larger horizon. The merged black hole is initially distorted, but it rapidly settles into a stable configuration through ring-down oscillations, shedding excess energy and angular momentum as gravitational waves. Gravitational wave astronomy has matured rapidly. LIGO and Virgo now detect mergers regularly dozens per year. Future detectors like the Einstein Telescope and Cosmic Explorer will increase sensitivity by an order of magnitude, detecting mergers throughout the observable universe. The space-based LISA detector, planned for the 2030s, will observe lower frequency gravitational waves from supermassive black hole mergers, extreme mass ratio in spirals, and other sources inaccessible to ground-based detectors. The cosmic horizon and observable universe. The universe extends far beyond what we can see. Light travels at a finite speed, and the universe has a finite age, approximately 13.8 billion years since the Big Bang. This combination creates a fundamental limit called the observable universe, a sphere centered on Earth with a radius determined not just by the age of the universe, but by its expansion history. The farthest objects we can observe are not 13.8 billion light-years away, but roughly 46 billion light-years distant, a seeming paradox resolved by cosmic expansion. When astronomers observe distant galaxies, they see them as they were billions of years ago. The light has been travelling toward us for that entire time. A galaxy observed at a distance of 10 billion light-years appears as it was 10 billion years ago, when the universe was only 3.8 billion years old. During the light's journey, the universe has continued expanding. The space between us and that galaxy has stretched, carrying the galaxy farther away even as its ancient light travels toward us. By the time the light arrives, the galaxy itself is much more distant than 10 billion light-years, perhaps 16 billion light-years or more, depending on the expansion history. The most distant observable objects are those whose light was emitted shortly after the Big Bang, during the era when the universe became transparent to radiation. Before this moment, roughly 380,000 years after the Big Bang, the universe was a hot, dense plasma of electrons and protons. Photons scattered constantly off free electrons, unable to travel far before being absorbed and re-emitted. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms in an event called recombination. Suddenly, photons could travel freely through space. This first light, now stretched by expansion into microwave wavelengths, is the cosmic microwave background radiation. The CMB represents the edge of the observable electromagnetic universe. We cannot see anything more distant because there was no transparent medium before recombination. No light could travel freely. The surface from which the CMB was emitted is now located approximately 46 billion light-years away due to the expansion that has occurred since. This defines the radius of the observable universe, a sphere containing roughly 2 trillion galaxies, though most are too faint and distant to detect individually. Beyond this horizon lies more universe, possibly infinite in extent, but it remains forever beyond our observational reach. Light from regions farther than 46 billion light-years has not had time to reach us, and due to accelerating expansion driven by dark energy, it never will. The expansion rate increases with distance. At sufficient distance, space expands faster than light can travel through it. This creates a cosmic event horizon, analogous to a black hole's event horizon but in reverse. Instead of nothing escaping from inside, nothing from outside can enter our observable region. The cosmic event horizon is not static. As the universe ages, it slowly recedes, allowing light from slightly more distant regions to eventually reach us. However, the accelerating expansion causes an opposite effect. Galaxies currently within our observable universe are being pushed beyond the cosmic event horizon, disappearing from view forever. In the distant future, as dark energy dominates more completely, only gravitationally bound structures, our local group of galaxies, will remain observable. Everything beyond will have receded past the horizon, leaving future observers in an apparently empty universe with only a few nearby galaxies visible. Measurements of cosmic expansion rely on multiple techniques. The Hubble constant, the current expansion rate, is measured by observing how fast distant galaxies recede. Type Ia supernovae serve as standard candles, their peak brightness known, allowing distance determination from apparent brightness. Baryon acoustic oscillations patterns in galaxy distribution left over from sound waves in the early universe provide another distance scale. The cosmic microwave background's detailed structure encodes information about the universe's geometry and expansion history. These methods agree reasonably well, though small discrepancies called the Hubble tension suggest our understanding may be incomplete. The ultimate fate of the observable universe depends on dark energy's nature. If dark energy remains constant, the cosmological constant scenario, the universe will expand forever at an accelerating rate. Galaxies beyond the local group will disappear beyond the cosmic horizon. Star formation will gradually cease as gas is exhausted. Existing stars will die, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will decay or evaporate. The universe will become cold, dark, and empty, the heat-death scenario. If dark energy strengthens over time, the Big Rip scenario expansion accelerates catastrophically. Eventually, expansion overwhelms gravitational binding at all scales. Galaxy clusters disperse first, then individual galaxies, then solar systems, then planets, and finally atoms themselves are torn apart as space expands faster than the forces holding matter together can resist. This would occur perhaps 20 to 30 billion years from now, though the exact timing depends on how rapidly dark energy strengthens. Alternatively, if dark energy weakens or reverses, perhaps transitioning to an attractive force expansion could slow, halt, and reverse, leading to the Big Crunch. The universe would collapse back on itself, galaxies rushing together, space contracting, temperatures rising, culminating in a singularity similar to the Big Bang, but in reverse. Current observations suggest this scenario is unlikely. The expansion is accelerating, not slowing. The shape of the universe also determines its ultimate extent. Observations indicate the universe is spatially flat, or very nearly so, meaning parallel lines remain parallel over cosmic distances. A flat universe is infinite in spatial extent. If slightly positively curved like the surface of a sphere, the universe would be finite, but unbounded. Travelling far enough in one direction would eventually return you to your starting point, though the distance would exceed the observable universe by many orders of magnitude. If negatively curved like a saddle, the universe would be infinite. Current measurements are consistent with flatness, suggesting infinite spatial extent, though only a finite portion is observable. The concept of the farthest point anything can reach in an expanding universe becomes nuanced. Light emitted from Earth today will eventually reach galaxies currently receding faster than light, because expansion is slowing in those regions. A photon travelling outward will eventually cross into regions where space expands more slowly than the photon's speed, allowing it to make progress. The farthest a photon emitted today can eventually reach is approximately 63 billion light-years in moving distance, the distance measured accounting for all future expansion. Regions beyond this will never be reachable by light emitted today, even given infinite time. Relativistic rockets and the light speed barrier. Travelling at speeds approaching light speed transforms the physics of motion in profound ways. A spacecraft accelerating continuously at a comfortable standard gravity, the same acceleration we experience on Earth's surface, could theoretically reach relativistic speeds, given enough time and energy. From the perspective of passengers aboard such a craft, the journey to distant stars would be compressed by time dilation, making interstellar travel feasible within a human lifetime, at least in principle. The mathematics of relativistic rocket travel reveals both possibilities and severe constraints. A rocket accelerating at one gravity would reach 90% of light speed after approximately 1 year of proper time as experienced by the crew. After 2 years, the speed would exceed 99% of light speed. Due to time dilation, however, observers on Earth would measure much longer durations. When the rocket reaches 99% of light speed from the crew's perspective, decades would have passed on Earth. The discrepancy grows more extreme at higher speeds. From the crew's perspective, distances contract in the direction of motion. A destination 10 light-years away would appear only about 1.4 light-years distant when travelling at 99% of light speed due to Lorentz contraction. This makes the journey seem faster from the crew's viewpoint. Combined with time dilation, a trip to a star 10 light-years away would take only about 1 year of proper time for the crew, if constant acceleration and deceleration at one gravity were maintained. The catch is that more than 20 years would pass on Earth during the same journey. The energy requirements are staggering. Accelerating 1 kilogram to 90% of light speed requires approximately 2.5 times 10 to the power of 17 joules, roughly the total energy output of a large nuclear power plant running for 1 year. A spacecraft with a mass of 1,000 metric tons would require 250 trillion times more energy. No known propulsion system can approach this efficiency. Chemical rockets are hopelessly inadequate. Nuclear fission and fusion offer improvements but remain far short of requirements. Antimatter annihilation converts mass to energy with 100% efficiency, making it theoretically ideal, but producing and storing antimatter in the required quantities is beyond current technology. The relativistic rocket equation governs the relationship between fuel mass, payload mass, and final velocity. Unlike the classical rocket equation where doubling the fuel roughly doubles the velocity increase, the relativistic version shows diminishing returns. To reach 90% of light speed using a perfect matter-antimatter engine, the initial mass of the rocket must be approximately 13 times the final mass, meaning 12 parts fuel for every 1 part payload. To reach 99% of light speed requires a mass ratio of about 50:1. To reach 99.9% requires approximately 350:1. The fuel requirements increase exponentially. Alternative propulsion concepts avoid carrying fuel entirely. A laser sail uses powerful ground-based lasers to push a lightweight reflective sail, accelerating a spacecraft without onboard propulsion. The laser remains on Earth or in solar orbit, beaming energy to the sail as it recedes. This approach eliminates fuel mass from the spacecraft itself, though it requires enormous laser arrays generating petawatts of power. Deceleration presents a challenge. The laser beam disperses over interstellar distances, and reversing momentum requires either a second laser at the destination or deployment of a separate braking sail. The Breakthrough Starshot initiative proposes using this concept to send gram-scale probes to Alpha Centauri, accelerating them to 20% of light speed with gigawatt lasers. At this velocity, the probes would reach Alpha Centauri in approximately 20 years, with data returning to Earth after an additional 4.4 years for the radio signals to travel back. The project faces immense technical hurdles, creating laser arrays powerful enough, building sails lightweight yet durable enough to withstand the laser beam, miniaturizing instruments to gram scale, and protecting the probes from interstellar dust impacts at relativistic speeds. Interstellar dust and gas become hazards at relativistic velocities. At 90% of light speed, a collision with a dust grain 1 mm in diameter releases energy equivalent to several kilograms of TNT. The kinetic energy increases with the square of velocity, so higher speeds make even microscopic particles devastating. Shielding adds mass, worsening the fuel problem. One proposed solution uses magnetic fields to deflect charged particles, but neutral dust grains pass through unaffected. Cosmic rays, high-energy particles pervading space, also become more intense from the perspective of a relativistic spacecraft. Normally, cosmic rays arrive from all directions with a range of energies. A spacecraft travelling at near-light speed experiences cosmic rays from ahead, blue-shifted to much higher energies, creating a deadly radiation environment. The crew compartment would need heavy shielding, adding mass. Time dilation offers a peculiar advantage for interstellar travellers willing to leave Earth behind. A spacecraft maintaining 1 gravity acceleration could theoretically reach the Andromeda Galaxy 2.5 million light-years away, in approximately 28 years of proper time from the crew's perspective. The journey would require flipping the ship halfway to decelerate at 1 gravity for the second half. On Earth, however, more than 2.5 million years would pass. The travellers would arrive in a future far beyond any recognisable civilization, having experienced only 3 decades of aging. This creates a form of practical one-way time travel into the future. Returning to Earth after such a journey would mean arriving millions of years after departure. The travellers would find a planet transformed beyond recognition, if it still exists. For this reason, relativistic journeys are essentially one-way trips through time as well as space. The faster the travel, the greater the time dilation, and the farther into Earth's future the travellers emerge. The light speed barrier remains absolute. No matter how powerful the propulsion, no massive object can reach light speed. As velocity increases, so does relativistic mass, requiring ever more energy for additional acceleration. The curve asymptotically approaches light speed but never reaches it. At 99.999% of light speed, the spacecraft's relativistic mass is 224 times its rest mass. At 99.9999%, it's 707 times. The progression continues without limit, each additional 9 adding a factor of roughly 3. Quantum entanglement and non-locality. Quantum mechanics introduces phenomena that seem to challenge the light speed limit, though on closer examination they preserve it. Quantum entanglement allows particles to share correlations that persist across arbitrary distances instantaneously. When two particles are entangled, measuring a property of one immediately determines the corresponding property of the other, regardless of separation. Einstein famously called this spooky action at a distance and thought it revealed incompleteness in quantum mechanics. Experiments over decades have confirmed that entanglement is real. Create two entangled photons and send them to opposite sides of the galaxy. Measure the polarization of one photon, and the polarization of the other is instantly determined. The correlation is perfect and instantaneous, faster than light could travel between them. Yet this doesn't violate relativity because no information is transmitted. The key distinction is between correlation and communication. When you measure the first photon, its polarization is random, you cannot control the outcome. The second photon's polarization is perfectly correlated, but equally random from that observer's perspective. Neither observer can determine whether the other has made a measurement. No message can be encoded or transmitted. The correlations only become apparent when both sets of measurements are compared, which requires communication through conventional channels limited by light speed. Attempts to exploit entanglement for faster-than-light communication inevitably fail. Proposed schemes involve pre-arranged measurement choices that could encode information, but quantum mechanics forbids this. The no-communication theorem proves that entangled particles cannot transmit information faster than light. The correlations are established when the particles are created, not when measurements occur. Measurement reveals pre-existing correlations, it doesn't create them instantaneously. This raises profound questions about the nature of reality. Bell's theorem shows that no local hidden variable theory can reproduce quantum mechanics predictions. Either the universe's fundamentally non-local measurements at one location instantaneously affect distant locations, or reality doesn't exist independently of measurement. Experiments called Bell tests have confirmed quantum mechanics predictions with ever greater precision, ruling out local hidden variables and confirming that nature is, in some sense, non-local. However, this non-locality doesn't permit faster-than-light signaling. The distinction between quantum non-locality and relativistic causality is subtle but crucial. Relativity prohibits information or causal influences from propagating faster than light. Quantum entanglement involves correlations but not causal influences in the relativistic sense. Measuring one particle doesn't cause the other's state to change. Both particles' states are correlated from the moment of entanglement. Quantum teleportation exploits entanglement to transfer quantum states between locations, without the state traveling through the intervening space. The protocol requires an entangled pair shared between sender and receiver, plus classical communication of measurement results. The quantum state is destroyed at the sender's location and recreated at the receiver's location, giving the appearance of teleportation. However, the classical communication step limits the process to light speed. The receiver cannot reconstruct the state without information sent conventionally from the sender. Quantum cryptography uses entanglement for secure communication. The correlations of entangled particles allow two parties to generate shared random keys that are provably secure against eavesdropping. Any attempt to intercept the quantum states disturbs them detectably. Commercial quantum key distribution systems operate over optical fibers and satellite links, securing communications with principles of physics rather than computational complexity. China's Mauritius satellite has demonstrated quantum entanglement distribution over thousands of kilometers. The entanglement distance record continues to grow. Photons entangled on Earth have been distributed between ground stations and satellites, maintaining correlations across distances exceeding 1,000 kilometers. In principle, entanglement persists. Regardless of distance, entangled particles separated by light years would remain correlated. The challenge is maintaining coherence and preventing decoherence from environmental interactions that break the delicate quantum correlations. Proposed quantum networks would link quantum computers through entangled connections, enabling distributed quantum computing and unhackable communication networks. The quantum internet remains largely theoretical, facing enormous technical challenges in creating and maintaining entanglement over large scales. Quantum repeaters devices that extend entanglement range by creating new entangled pairs and swapping entanglement between them are in early development. A functional quantum internet would revolutionize cryptography, sensing, and computation, though it would still be bound by light speed for classical communication. Entanglement's role in the EPR paradox, named for Einstein, Podolsky, and Rosen, continues to puzzle physicists. The paradox questions whether quantum mechanics provides a complete description of reality. If measuring one particle's position instantly determines the other's, and measuring its momentum instead determines the other's momentum, then both properties must have definite values before measurement, contradicting quantum mechanics' uncertainty principle. Bell's theorem and subsequent experiments show that quantum mechanics is correct and local realism is wrong. Either locality fails or realism fails, properties don't have definite values before measurement, or both. The farthest reach of quantum entanglement is unlimited by distance but constrained by coherence. Entangled states are fragile, easily disrupted by interactions with the environment. Maintaining entanglement over cosmic distances would require isolating the particles from all environmental influences, a practical impossibility given the pervasive cosmic microwave background, interstellar gas, and magnetic fields. For entanglement to persist, the particles must remain quantum mechanically isolated, yet any measurement or use of the entanglement involves interaction, which typically destroys it. Dark energy and the accelerating universe. In 1998, observations of distant Type Ia supernovae revealed that the universe's expansion is accelerating rather than slowing as previously assumed. This discovery, honored with the 2011 Nobel Prize in Physics, introduced dark energy, a mysterious component comprising approximately 68% of the universe's total energy density. Dark energy opposes gravity on cosmic scales, pushing space to expand faster over time, fundamentally altering the universe's fate and redefining the farthest points anything can reach. Type Ia supernovae occur when white dwarf stellar remnants composed of carbon and oxygen accrete matter from companion stars until they reach the Chandrasekhar limit of about 1.4 solar masses. Unable to support their own weight, they collapse and explode in thermonuclear detonations. The explosion's peak brightness is remarkably consistent, making these supernovae standard candles for measuring cosmic distances. By comparing apparent brightness to known intrinsic brightness, astronomers determine distance. Two independent teams studying distant supernovae expected to measure how much cosmic expansion was slowing. Gravity from all matter should decelerate expansion, so older, more distant supernovae should appear brighter than predicted. By a constant expansion rate, they would be closer than expected. Instead, the supernovae appeared dimmer, indicating they were farther away. The expansion was accelerating, not decelerating. Something was pushing galaxies apart, overpowering gravity's pull. The simplest explanation is Einstein's cosmological constant, a term he introduced in 1917 to create a static universe, balancing gravity's attraction. When Hubble discovered cosmic expansion in 1929, Einstein abandoned the cosmological constant, allegedly calling it his greatest blunder. The 1998 discovery rehabilitated it. The cosmological constant represents energy inherent to empty space itself. As space expands, more space appears, bringing more energy. Unlike matter or radiation, which dilute as the universe expands, dark energy's density remains constant, so its influence grows relative to matter as the universe ages. The physical origin of dark energy remains mysterious. Quantum field theory predicts vacuum energy from quantum fluctuations, particles and antiparticles spontaneously appearing and annihilating in empty space. Calculating this vacuum energy yields a value approximately 10 to the power of 120 times larger than the observed dark energy density. Perhaps the worst prediction in physics history. This enormous discrepancy, called the cosmological constant problem, suggests fundamental misunderstanding of quantum field theory, gravity, or both. Alternative models propose dynamical dark energy whose density changes over time. Quintessence, named after the classical fifth element, is a hypothetical scalar field that pervades space, its energy density varying as it evolves. Unlike the cosmological constant, quintessence could strengthen, weaken, or even change sign over cosmic time. Observations constraining how dark energy has changed over the universe's history find results consistent with a constant. though small variations remain possible. Dark energy's effects depend on spatial scale. Within gravitationally bound systems like galaxies or galaxy clusters, dark energy's influence is negligible compared to gravity. The Milky Way and Andromeda will merge as scheduled despite dark energy. The local group of galaxies remains bound. Only on scales of hundreds of millions of light-years does dark energy dominate, overwhelming the gravitational attraction between galaxy clusters and superclusters. The expansion rate is measured by the Hubble constant, currently about 70 kilometers per second per megaparsec. This means galaxies separated by 1 megaparsec, 3.26 million light-years, recede at 70 kilometers per second due to expansion. At 10 megaparsecs, they recede at 700 kilometers per second. At sufficient distance, recession velocity exceeds light speed. This doesn't violate relativity. The galaxies aren't moving through space faster than light. Space itself expands, carrying them apart. The observable universe's boundary is defined partly by this effect. Light from galaxies whose recession velocity exceeds light speed is redshifted so severely that wavelengths stretch toward infinity. The cosmic event horizon marks the maximum distance light can travel over all future time. Galaxies beyond this horizon will never be observable, even given infinite time, because space between us expands faster than light can cross it. Currently, galaxies beyond about 16 billion light-years recede faster than light. The cosmic event horizon lies at approximately 63 billion light-years in co-moving coordinates that expand with space. Light emitted today can eventually reach galaxies within this distance, though the journey takes dozens of billions of years as the photon climbs out of the expanding space. Galaxies beyond 63 billion light-years will never receive light emitted from Earth today. This shrinking reachability has profound implications. In the far future, as dark energy dominates more completely, the cosmic event horizon contracts. Galaxies currently within reach slip beyond it permanently. Distant galaxy clusters already beyond communication range recede faster, fading from view as their light redshifts into the infrared, microwave, and eventually radio wavelengths before becoming undetectable. In trillions of years, only the local group gravitationally bound and immune to expansion will remain visible. Future observers in such a universe, having no knowledge of our current observations, might conclude the universe contains only their local galaxy group surrounded by empty space. The cosmic microwave background would have redshifted beyond detectability. Distant galaxies would have disappeared. Evidence for the Big Bang and cosmic expansion would be erased by expansion itself. This highlights the importance of cosmological observations. Today we live in a privileged epoch when the universe's history remains accessible. Dark energy's ultimate strength determines the universe's fate. If constant, expansion accelerates gradually, leading to the heat death scenario where the universe becomes cold, dark, and empty over trillions of years. If dark energy increases, the phantom energy scenario acceleration intensifies, potentially leading to the Big Rip where expansion overwhelms all forces, tearing apart galaxies, stars, planets, and eventually atoms. If dark energy decreases or reverses, expansion might slow, halt, or reverse into contraction, though current observations make this unlikely. Measuring dark energy's properties drives major observational programs. The Dark Energy Survey maps hundreds of millions of galaxies, measuring how cosmic structure has evolved. The Euclid Space Telescope and the Vera Rubin Observatory will survey billions of galaxies, precisely constraining dark energy's equation of state, the relationship between its pressure and density. These observations will determine whether dark energy is truly constant or varies over time, testing whether it matches the cosmological constant or requires new physics. Multiverse and eternal inflation. Cosmic inflation, a brief period of exponential expansion in the universe's first fraction of a second, explains several otherwise puzzling features of the cosmos. It explains why the universe is so uniform on large scales, why it's geometrically flat, and why no magnetic monopoles or other exotic relics from earlier phases exist. Inflation stretches a tiny patch of space to enormous size, smoothing irregularities and setting initial conditions for the Big Bang's hot, dense phase. Most evidence supports inflation, though alternative theories exist. Eternal inflation extends this concept in a remarkable direction. In most inflationary models, Quantum fluctuations during inflation create density variations that eventually become galaxies and galaxy clusters. Some regions fluctuate upward in the inflaton field, the hypothetical field driving inflation, while others fluctuate downward. Regions fluctuating downward exit inflation, transitioning to the hot Big Bang. Regions fluctuating upward continue inflating exponentially. This creates a patchwork cosmos. Some regions stop inflating and form universes like ours. Other regions keep inflating, exponentially expanding and generating more quantum fluctuations, which create more regions that exit inflation. The process becomes eternal and self-reproducing. Once inflation starts anywhere, it continues forever in some regions, spawning an infinite number of post-inflationary bubble universes embedded in an eternally inflating background. Each bubble universe is causally disconnected from others. The space between bubbles expands so rapidly that light or any signal from one bubble can never reach another. Each bubble undergoes its own Big Bang, develops its own galaxies, stars, and planets, potentially with its own physical laws if different symmetry breaking occurs during the transition from inflation. Our observable universe is one such bubble, a finite region within an infinite multiverse. The measure problem plagues eternal inflation. If infinitely many bubble universes exist, and infinitely many contain observers, how do we calculate probabilities? Infinity divided by infinity is undefined. Asking, what is the probability our universe has certain properties, becomes meaningless without specifying how to count universes. Different counting methods, different measures, give contradictory answers. Physicists debate which measure, if any, is correct. String theory adds another layer to the multiverse concept. String theory requires extra spatial dimensions beyond the familiar three. These extra dimensions must be compactified, curled up at tiny scales. The number of possible compactification shapes is staggeringly large, possibly 10 to the power of 500 or more. Each shape corresponds to a different vacuum state with different physical laws, different particle masses, coupling constants, and force strengths. This landscape of vacua suggests that different bubble universes might realize different string theory vacua, each with unique physics. The anthropic principle becomes relevant here. If infinitely many universes exist with different physical laws, most are sterile, incapable of supporting life. Perhaps only a tiny fraction have the precise properties needed for stars, planets, chemistry, and biology. We necessarily find ourselves in one of the rare hospitable universes because we couldn't exist in the others. This explains apparent fine-tuning the cosmological constant smallness, the strength ratios of fundamental forces, the mass of the Higgs boson not through fundamental principles but through selection effects. Critics argue this abandons predictive power. If any observation can be explained by invoking the multiverse and anthropic selection, the theory becomes untestable. Proponents counter that the multiverse is a consequence of well-motivated theories, inflation and string theory developed for other reasons. If those theories are correct, the multiverse follows inevitably. Moreover, anthropic reasoning makes testable predictions. It suggests the cosmological constant should be near the maximum value compatible with galaxy formation, which roughly matches observations. Observable consequences might exist. Bubble collisions could leave imprints on the cosmic microwave background circular patterns of enhanced or reduced temperature fluctuations. Searches for such patterns have found no convincing signals, constraining how frequently bubbles collide. Gravitational waves from bubble collisions might also be detectable, though distinguishing them from other sources is challenging. The mathematical multiverse hypothesis, proposed by physicist Max Tegmark, suggests that all mathematically consistent structures exist as physical realities. Our universe is one mathematical structure among infinitely many. This elevates the multiverse to maximum generality, not just bubbles with different physical constants, but universes with entirely different mathematical laws, different numbers of dimensions, different logical structures. This remains highly speculative and arguably beyond science's scope, straddling the boundary between physics and philosophy. The many worlds interpretation of quantum mechanics proposes yet another form of multiverse. Every quantum measurement causes the universe to split into branches, each realizing one possible outcome. All possibilities occur in different branches. Schrödinger's cat is both alive and dead, but in separate universes. This interpretation resolves the measurement problem without wave function collapse, but at the cost of exponentially proliferating universes, every quantum event creating countless new branches. Different multiverse concepts exist at different levels of speculation. Eternal inflation is a prediction of well-tested inflationary models. The string landscape follows from string theory's mathematical structure, though string theory itself lacks experimental confirmation. The quantum many-worlds interpretation is an alternative to standard quantum mechanics, equally consistent with experiments but philosophically distinct. The mathematical multiverse is more philosophical than scientific. Each level involves increasing speculation and decreasing testability. The farthest reach of the multiverse concept is literally infinite. If eternal inflation is correct, the totality of existence is infinitely large, containing infinitely many bubble universes, almost forever beyond our causal horizon. The farthest anything from our universe can reach is the boundary of our bubble, the region where inflation ended and our Big Bang began. Beyond lies the eternally inflating space, inaccessible and unobservable, generating new universes continuously. The final parsec problem and galactic nuclei. When two galaxies merge, their central supermassive black holes eventually sink toward the center of the merged galaxy through dynamical friction gravitational drag from stars and gas. The black holes form a binary, orbiting each other while spiraling inward. This process slows dramatically at a separation of about 1 parsec 3.26 light-years. At this distance, the binary has ejected most nearby stars on intersecting orbits, creating a depleted core. Without stars to scatter, the binary's orbital decay stalls. This is the final parsec problem. The problem is significant because gravitational wave emission becomes efficient only at much smaller separations. For solar mass black holes, gravitational waves dominate at separations of thousands of kilometers. For supermassive black holes containing millions or billions of solar masses, the transition occurs at distances of 10 to 100 million kilometers, 0.00007 to 0.0007 parsecs. If binaries stall at 1 parsec, they should take longer than the age of the universe to merge. Yet observations suggest supermassive black holes merge within timescales of billions of years. Several proposed solutions exist. Repopulation of the lost cone occurs if stars scatter off a massive perturber, like a third black hole or dense star cluster, sending them onto orbits intersecting the binary. These stars extract orbital energy from the binary, continuing its spiral. Simulations show this can work if the galactic nucleus contains enough stars and sufficient triaxiality deviation from spherical symmetry to sustain scattering. Gas accretion provides another mechanism. If the merged galaxy retains substantial gas, the black holes accrete matter, gaining mass while losing orbital angular momentum to the gas through viscosity and gravitational torques. The gas forms a circumbinary disk surrounding both black holes. Interactions between the binary and the disk drive orbital decay. This process is efficient if enough gas reaches the galactic nucleus, which depends on the merger's dynamics and whether gas is funneled inward or expelled. Gravitational slingshot assists occur when the binary encounters a third black hole or massive star cluster. The three-body interaction can eject the interloper at high velocity while tightening the binary's orbit. Repeated interactions could shrink the separation below 1 parsec, allowing gravitational wave emission to finish the merger. This mechanism is plausible in galaxies with multiple nuclear black holes from successive mergers. Eccentric binaries may overcome the stall more easily than circular ones. Eccentric orbits bring the black holes closer at periastron, the point of closest approach, enhancing gravitational wave emission. Eccentricity also increases the effective scattering cross-section with stars, maintaining dynamical friction longer. Some formation scenarios naturally produce eccentric binaries, potentially bypassing the final parsec problem. Observational evidence for supermassive black hole binaries comes from several sources. Periodic quasar variability suggests orbital modulation from binary black holes whose accretion rates vary as they orbit. Dual-active galactic nuclei in merging galaxies show 2 distinct X-ray or radio sources, indicating 2 black holes in the same system, though often separated by kiloparsecs rather than parsecs. Gravitational wave detections from merging supermassive black holes would provide definitive evidence, but require space-based detectors like LISA, planned for the 2030s. The pulsar timing array method uses millisecond pulsars, ultra-stable rotating neutron stars as a galaxy-scale gravitational wave detector. Gravitational waves from distant supermassive black hole binaries stretch and compress space, subtly changing distances to pulsars and affecting pulse arrival times. By monitoring arrays of dozens of pulsars for years, astronomers search for correlated timing variations indicating gravitational waves. Recent results suggest possible detection of a gravitational wave background from many distant binaries, though confirmation requires more data. The outcome of a supermassive black hole merger depends on the mass ratio and spins. Comparable mass black holes with spins aligned or anti-aligned merge relatively symmetrically, producing a single black hole with mass equal to the sum minus a few percent, radiated as gravitational waves. The final black hole's spin depends on the initial spins and orbital angular momentum. Extreme mass ratios produce less symmetric mergers, with the smaller black hole spiraling into the larger one, creating a prolonged gravitational wave signal. Recoil velocities from asymmetric mergers can eject the final black hole from its host galaxy. When two black holes with different masses or spins merge, the gravitational waves carry net momentum, kicking the final black hole in the opposite direction. Simulations show recoil velocities can exceed 1,000 km per second faster than escape velocity from most galaxies. Observational searches for offset or wandering supermassive black holes have identified candidates, though confirmation is difficult. Gravitational wave recoil affects galaxy evolution. If the central black hole is ejected, the galaxy lacks a nuclear black hole for millions of years until another form or a wandering black hole returns. This affects star formation in the nucleus, disrupts the relationship between black hole mass and galaxy properties, and potentially creates galaxies with off-center black holes or binary systems from multiple ejections and returns. The final parsec problem intersects with the question of how fast supermassive black holes can travel. A recoiling black hole escapes its galaxy if kicked faster than escape velocity, typically 500 to 1,000 km per second for massive elliptical galaxies. Ejected black holes become intergalactic wanderers, travelling through the voids between galaxies. Over billions of years, they slow due to gravitational interactions with cosmic structures, possibly becoming captured by other galaxies or halting in intergalactic space. The farthest such a black hole could reach depends on its kick. The ultimate limit. The farthest point anything can reach is not defined by a single distance or boundary, but by the interplay of fundamental physical limits. Escape velocity increases with proximity to massive objects, reaching the speed of light at a black hole's event horizon. Beyond this, even light cannot escape. The event horizon represents an absolute limit, a one-way boundary from which no information or matter can return to the external universe. Yet even the event horizon is not the final frontier. Inside, the structure of spacetime leads inevitably to the singularity, where curvature becomes infinite and general relativity ceases to provide meaningful predictions. Whether singularities are real or artifacts of ignoring quantum effects remains unknown. A theory of quantum gravity may reveal that singularities are replaced by regions of extreme but finite curvature, perhaps involving spacetime at the Planck scale. The speed of light itself imposes a cosmic speed limit, preventing anything with mass from reaching or exceeding it. This limit is not merely technological but fundamental, a consequence of spacetime's structure. To accelerate a massive object to light speed would require infinite energy, an impossibility. Only massless particles like photons travel at this ultimate speed, and they do so always, experiencing no passage of time. For light, the journey to the farthest point it can reach depends on the curvature of spacetime. In flat spacetime, light travels indefinitely, covering infinite distance given infinite time. Near a black hole, light can orbit at the photon sphere or fall into the event horizon. In the expanding universe, light emitted from distant galaxies is carried away by cosmic expansion, eventually receding faster than light can travel toward us, not because the light exceeds light speed locally, but because the space between us and the source expands faster than light can cross it. The observable universe, the region from which light has had time to reach us since the Big Bang, is finite, with a current radius of about 46 billion light-years. This is the farthest point from which we can currently receive information. Beyond this cosmological horizon, light has not had time to reach us. As the universe ages and expands, this horizon grows, but accelerating expansion driven by dark energy causes distant regions to slip beyond the horizon permanently, becoming forever unreachable. In terms of escape velocity, the ultimate limit is the edge of the causally connected universe. Within this boundary, events can influence each other. Beyond it, no signal, no matter, no information can cross. This boundary is not a physical barrier, but a limit imposed by the finite age of the universe and the finite speed of light. The farthest point anything can reach, then, is determined by a combination of factors: the speed of light, the curvature of spacetime, the mass distribution of the universe, and the expansion driven by dark energy. For a photon escaping a black hole, the farthest it can reach is just beyond the event horizon if it starts inside. It reaches nowhere beyond the singularity. For a spacecraft launched from Earth, the farthest reachable point depends on available energy, gravitational assists, and the time available before cosmic expansion makes distant regions unreachable. Human exploration faces additional limits. No known propulsion can accelerate a spacecraft to a significant fraction of light speed. Even at 10% of light speed, reaching the nearest star would take over 40 years. Intergalactic travel would require many millions of years at such speeds. Faster travel demands either breakthroughs in physics manipulating spacetime itself through mechanisms like warp drives or multi-generational journeys on timescales longer than human civilizations have existed. From a practical standpoint, the farthest anything from Earth can reach within a human lifetime is limited to the solar system and perhaps the nearest stars. From a theoretical standpoint, light and hypothetical massless particles can reach the edge of the observable universe given enough time. From a fundamental standpoint, the farthest point anything can reach is the boundary beyond which spacetime's structure prevents further progress, the event horizon for objects near black holes, the cosmological horizon for light in an expanding universe, and the Planck scale for inquiries into the nature of spacetime itself. The journey to the farthest point anything can reach is not a single path but a multitude, shaped by gravity, velocity, and the fabric of reality. It's a journey that spans from the surface of Earth to the edge of the cosmos, from the event horizons of black holes to the quantum foam of spacetime, from the predictable trajectories of Newtonian mechanics to the strange, warped geometry of general relativity. At each step, the limits are defined not by barriers but by the fundamental laws governing motion, energy, and the structure of the universe itself.